Welcome to the second part of the lecture on arrays in C. So today, first we will discuss about two-dimensional arrays in C. We will see how one can do various kinds of processing on a two-dimensional array, and after that, we will look at how two-dimensional arrays can be passed as an argument to a function, and finally, we will have a very abstract discussion on multidimensional arrays. Table of values. Many programming problems require to maintain a table of elements of the same data type. For example, programs to maintain and process matrices. So, matrix can be viewed as a table of values of the same kind. So, what C provides to process a matrix is a two-dimensional array. So, here the figure shows a two-dimensional array, namely T, with 4 rows and 5 columns, which can store 4 into 5 is equal to 20 elements. Just like single dimensional array, here again an element can be accessed using indexing the indices in the array, but it's a two-dimensional array, and if there are n rows and n columns in the two-dimensional array or matrix, then row index and column index are respectively taken from these two intervals. So here is in this example, there are 1, 2, 3, 4 rows, and the row index varies from 0 to 3, which is 4 minus 1. And the columns, here there are 5 columns, and the column index varies from 0 to 4. And how will you access an element? An element in T can be accessed using this syntax. That is, you need to provide two indices, I and j. And what is the value of I? I is a raw number, here varies from 0 to 3, and j is the column number, varies from 0 to 4 in this example. In general, if it's an m by n matrix, then the I values range from 0 to m minus 1, and j value ranges from 0 to n minus 1. For example, see how will you access this element? This element is in the second row and third column, so can be accessed by T 2 3. Yeah, that's the syntax for accessing this element. So T followed by the first index, that is the row index, followed by the column index. So this figure shows the indices of different elements in this example array. So in the first row, the row number is 0 in all the cells. Similarly here 1, 2 and 3. And if you look at a column, the first column, the column number is 0. Similarly 1, 2, 3 and 4. So it's very easy to find the indices to access an element, and the row number and column number starts with 0. So memory allocation for two-dimensional array. See an example function foo, which declared an array, two-dimensional array T or a matrix T of 2 rows and 3 columns. And the purpose of this example is just to understand how memory is allocated for a two-dimensional array. Let us see. So the function is invoked. So the creation of an instance of foo requires to allocate a sequence of 6, which is 2 into 3 consecutive memory locations. So each element is assumed to we start in 2 consecutive bytes. So the total number of bytes is 12, with this assumption that 2 bytes are required for an integer. And the elements can be accessed by using the row index and column index. So for the first element, the row index is 0, column index is 0, and it goes like that. You can see how the indices varies. Okay. And this array, which is stored in memory as a sequence of consecutive locations, can be drawn as this kind of two-dimensional object, which is a matrix. Just like a single dimensional array, here again the name of the array represents the starting address of the array in the memory, in this case 500. So more about memory allocation for an array. So here for T there are 2 rows and 3 columns. So in total 6 elements needs to be stored. So it allocates memory for 6 integers. So if you look at this memory allocation, you can see that it is not different than creating a single dimensional array of size 6. So memory allocation for an array with 2 rows and 3 columns is just like for a single dimensional array of 6 elements. But if you declare an array using this syntax with 2 rows and 3 columns, then you can access the array using 2 indices. That's a virtual view, or which has nothing to do with the layout in memory. So regardless of whether an array is single dimensional or 2-dimensional, a sequence of n locations are required. Okay, and the location, I mean the number of bytes required for each element. So you can see that this is actually a collection of 2 single dimensional array. You can see that the first row is a single dimensional array, which is T0. So naturally, what will be the syntax for accessing this element? The array is T0, so T00. This is T01, this is T02. So a 2-dimensional array of m rows and n columns can be viewed as m single dimensional array of size n each. Anyway, for a programmer need not have to worry about how exactly memory is allocated. What the programmer should know is how can she or he refer to an element in the 2-dimensional array. So it's by using 2 indices I and j. If T is the array, Tij should be the syntax, and the value of I ranges from 0 to number of rows minus 1, and the value of j ranges from 0 to number of column minus 1. So now, what is the formal syntax for declaring a 2-dimensional array? So here is the syntax, and see the various parts in it. So first is the data type, which is the data type of the elements in this array. All the elements must be of the same type, and this is that data type. Followed by the name of the array, then followed by the specification of the number of rows and number of columns. And these must be positive integer constants. And as we discussed, for single dimensional array, you can use symbolic constants also. Then how to access a 2-dimensional array? Here is the syntax, and the components are the array name followed by the indices, and the index values. The I is the row index, so varies from 0 to number of rows minus 1, and j is the column number and ranges from 0 to number of columns minus 1. Now see how can we process a two-dimensional array. Sequencing through a two-dimensional array. So consider a two-dimensional array with 4 rows and 5 columns, and these are the indices of the elements in this array. Let us see how we can process the elements of this array in a systematic order. So maybe one can process it column by column or row by row. So we will be looking at a systematic order in the order of rows. So first we will be processing row 0, then row 1, then likewise until we reach the last row. Okay, see how we can do it. So we can start with the first element of the first row, and the indices are row index 0 and column index 0. So because row wise, now we need to move to the next element in that row, so the column index needs to be incremented. So j is incremented to 1, and likewise you move all the way till you reach the last element of the first row. So the first row is finished. So what to do now? Now you need to move to the next row. For that, the row index needs to be incremented and reset the column index to 0. Yeah. So now the row index is 1 and column index is 0. Now you process all the elements in that row just like a single dimensional array. So increment the column index until you reach 4. Okay, so now the second row is processed. Similarly, you go and process the third row. Yeah, and finally you again increment the row index to move to the next row and replace this date to the first element of that row, and now you finish processing that row. So that's it. So if you recollect what we did, initially we initialized the row index to 0, and we moved all the way to the right in this row. That is, the value of j is is varied from 0 to 4, which is the number of columns minus 1. So the row index is fixed as 0 in this row, and the column index is varied to access this element, and then we position the row index to 1, and you process that by varying the column index again from 0 to 4. Similarly, the next row, and finally the last row. Okay, so we need to first set I as 0, then for I is equal to 0, move from 0 to 4 for j. Let us see how we can formulate or write this as a chord using for loops. So sequencing through a two-dimensional array using for loops. So we know that to process a row, we need to vary the value of j from 0 to 4, which is less than 5 is 4, up to 4. Okay, regardless of in which row you are, you need to move or you need to process all the elements in that row. For that, the column index must be varied from 0 to 4. Okay, now what about the row index? So you have to do this for each value of I from 0 to 0 to, it should be, sorry, there's a mistake, this should be 4. You read it as 4. Okay, you need to move in this interval, so this should be 4. Okay, so this is the syntax for accessing, for doing a systematic processing of a matrix, where in the outer loop you vary the row index, and for each row you vary the column index from 0 to number of columns minus 1. Okay, so here there is a typo, it should be 4. So uh, I think this structure of the code is clear to all of you. So basically, it is for I is equal to 1, uh, 1 to m. If there is this is an m by n matrix, vary the value of phi from 0 to m minus 1, and vary the value of j from 0 to n minus 1. Okay. So for I is equal, I is the raw number and j is the column number. So for I is equal to 0 to m minus 1, and for j is equal to 0 to n minus 1 for a matrix of order m by n. Let us see how you can read elements to a matrix. So here in the example, 4 rows and 3 columns. So I varies from 0 to 3, 4 minus 1, and j varies from 0 to 2, which is 3 minus 1. So what kind of a processing you need for each element is just read it. So if you execute this part of the code, this message will be printed, and assuming that the user has given these values, if you process this code, this matrix will be transformed into this state. That these values are getting stored in the matrix. Okay, so that's how you read elements. So remember that what we did is the processing is just reading. That's it, and this loop structure is same regardless of what kind of processing you do. So now you see how can you display the content of a matrix. So here the processing is just printing the value. That's it. That's the only change. And a printf statement is added here to go to the next line. That's it. /n means you break the line and go to the next line. Just otherwise, all the elements will be printed in the same line. So after arrow, you go to the next line. That is the purpose of this statement. Okay. And if you execute this part of the code, and what will happen in the screen, this will be printed like whatever we said here. And because we are not altering the elements, the matrix is not getting altered. Okay. Okay, see what this part of the code is doing. So this is the systematic processing of the elements. So what we are doing is each element is now modified. In what way it is modified? 10 is added to each of the elements here. So if you execute this part of the code on this matrix, then you will get this. So 10 is added to each position. Okay, 10 is added to the element at every position. Okay. Yeah, now let us see how can we add two matrices. So we know that to add two matrices, both the matrices must be of the same dimension. Here the matrix A is of dimension 4 by 3 and B is of dimension 4 by 3. So you can add these two matrices and then you will be getting a matrix of the same order, which is 4 by 3. Okay, then what will be the code to add these two matrices to give the resulting matrix? So how many rows are there in the result required in the resulting matrix? 4, same as the number of rows here, and 3 columns. So we know what will be the structure of the code. For I is equal to 1 to 3 and for j is equal to 1 to 2. Yeah, that's it. For I is equal to 1 to 3, that is less than 4. for j is equal to 1 to 2, that is less than 3, we want to find Cij. So, but we need to find what will give you Cij for each I and j here. Look at some examples. So this is C0, 0. So what will be the value? It's nothing but the sum of these values, right? That is A0, 0 plus B0, 0. So that's it. Let's look at another position. And here we want to find the value at 2, 1. So what will be that? What will give you the value here is nothing but the sum of the corresponding elements in this matrices. So it's this element plus this element. And how will you write it? It's A21 plus B21. Okay, B21. That's it. So now maybe it's enough to generalize. How will you find each value? Cij. So we want to add the corresponding values in these matrices. So Cij is equal to Aij plus Bij for all values of I from 0 to 3 and all values of j from 0 to 2. So what is required here is Aij plus Bij. So that is the code. Yeah, now we got it. So this is the code for finding the sum of two matrices, if at all the matrices can be added. And if you perform this code, or if you execute this code on these two matrices, you will get this resulting matrix. Okay, so we just look at an example. So in general, what will be the values required here? So if the matrix is of order m by n, we know that all the matrices must be of the same order. Then the value of I is the raw number varies from 0 to m minus 1 number of rows, and j from 0 to n minus 1 and is the number of columns. Okay. So another problem. Now the question is, how will you multiply two matrices? So you know that to multiply a matrix A with another matrix B, the number of columns here 3 of the first matrix must be equal to the number of rows of the second matrix. So 3 columns here, 3 rows here. So these two are two matrices which can be multiplied in that order, A into B. So what will be the order of the resulting matrix? If we multiply a matrix A of order m by n and B of order n by p, we know that the order of the resulting matrix will be m by p. M, which is the number of rows of the first matrix, and p, which is the number of columns of the second matrix. Here it is 2 and 2. So 2 by 2 matrix is what we are going to get. So it's C with 2 rows and 2 columns. How you are getting this 2? This is the number of rows of this matrix. This 2, which is the number of columns of this matrix. Now we need to find the code required here to multiply. Maybe we can try to look at the formula for finding the value of each element. We know that to find a matrix of this kind, we need a loop structure of this kind. So 2 rows and 2 columns. We need to know how can you define Cij for each value of I and j. Okay, let us look at the first element. How will you find this? To find this element, you need to process the first row of matrix A and first column of matrix B. Yeah, that's it. And what is the formula? It's 2 into 2 plus 3 into 3 plus 1 into 4. And if you write that in terms of indices, it's A00 into B00, yeah, plus A01, which is this element, into B10, which is this, and the third element, the processing of the next product is like this element into this element, that is A02, A02 into B20, B20. Yeah, so that is how you will find the first element. What about the second element? So you are processing this row and this column. You can see that it is A00, the same element as here, into B10. Sorry, B01. Okay, and A01 into B11. Yeah, plus A02 into B21, A02 into B2. Yeah. Next element, which is by taking this row and this column. So what is the first? A10 into B01, sorry, B00, A10 into B00 plus A11, A11 into B10, B10 plus A12. This element is A12, A12 into this element, which is B20. Yeah, B20. So next element is by taking this row and this column. So this is A10 into B01, B01 plus this element, which is A11, yeah, A11 into this element. What is that? B1, yeah, B11 plus this element, which is A12, yeah, A12 into this element, which is B21, yeah, B2. So that's how you can find the values in this particular example. And if you carefully analyze these formulas, you can observe that if you find the value Cij, where the row index is given in red color and column index is given in blue color. So you can see that from the A array, if you look at any row, the A value is taken from the same row index, see, A0, A0, A0. And the B element is taken from the same column index as this, B0, B0, see, B0. Okay, so at every row you can see that the row index of the A element, if you look at all the positions here, is same as the row index here, and the column index of the B element, that is the second index of the B element, in all the cases, this is blue color is same as this. Okay, maybe you can carefully look at this offline. So if you go deep in this, you can observe that if you look at a product, so what is it? And we show that the row index of A element is I, which is same as this I, and column element, which is J of B, is same as this J. Okay, it's like AI 0 B0 J. If you want to find Cij, it is AI 0 into B0 J plus AI1 into B1 J plus AI2 into B2 J. So what we observe is that each product is of the form AIK into BKJ. So here I value is same in all the position and J value is same as this INJ. Okay, AI k into bkj, and these two values are same that we found 0, here is 1, and here it is 2. So what is the value of k? K is 0 here, 1 here in this product, and 2 here in this product, and that's true for all the elements here. So the value of k ranges from 0 to 2, and that 2 is nothing but the number of okay, we will see that. So sorry, we see value of k ranges from 0 to 2, and what is that? 0 to 2 means 0, 1 and 2, 3 values, and which is given by the common value here, that is 3 columns of this matrix, which is same as 3 rows of this matrix. So the value of k ranges from the number of represents the number of columns of the first matrix, which is same as the number of rows of the second matrix. Okay, so that's it. So now we need to replace this with the code, required code. Okay, so the product is of the form aik into bkj, where the value of k must be varied from 0 to n minus 1, where n is the number of columns or the number of rows here. Yeah, so the code is, so remember we had this, only this part of the code is what we are substituting, we are not changing this, which is what we did is, I will tell you later what is this, now you just forget about this. This is for k is equal to 0, k less than 3, k plus plus. So what is this 3? The number of columns of this matrix, which is same as the number of rows of this matrix. And see that for each element we need to add these 3 elements, and the sum needs to be assigned here. How will you find the sum of n elements in using a code? First you assign the sum as 0, okay, sum as 0. Then you assign the first element, which is this one, to 0. So only this element is now there in Cij. After that you find this element, that is this, and add to the existing value of the sum, which is this element. If you carefully look at that, you can see that what we are doing for every row is, initially the value in the sum is initialized as 0, then you add this by using the value of k as 0, okay, then you add this by using the value of k as 1, and then you add this by using the value of k as 2, okay. So maybe you can look at it offline more carefully, and that is how you multiply two matrices when it is possible. Yeah, so this is the code, the same code, and if you perform this on these two matrices, you will get the value as shown here. So if you generalize, when the A matrix is order m by n, we know B matrix must be of order n by something and n by p, then this is the structure. I varies from 0 to m. J varies from 0 to p. We know that the resulting matrix is going to be of order m by p, that is why. And the value of k ranges from 0 to n, which is the number of columns of this matrix, same as the number of rows of this matrix. Okay, that's how you multiply two matrices. So now see how a two-dimensional array can be passed as an argument to a function, which is same as how a one-dimensional array is passed, which we already discussed in detail in the previous lecture. So I'm not spending time on this slides, very same, and the only difference is in the declaration of the formal argument. And not that here only the address of the array is passed to the call function. So no copy is created. Now copy of the matrix is created. The same matrix is shared between the called function and the calling function. as in the case of a single dimensional array. So here is the syntax for passing a two-dimensional array to a function, and the syntax is same as for a one-dimensional array. Here is a function name, which is a function to be called, and the array name must be given in parentheses. So square brackets are not required, and so just the array name, same as in the case of a single dimensional array. You know, array name represents the starting address of the memory allocated to the array, and because this address is passed, the same array instance is shared between the calling function and the called function. And now look at the syntax for declaring the formal argument. The components are the data type of the function which is being defined or called. So this is the data type of the value to be returned by this function, and the function name. So here is the data type of the array to be received. That is the data type of the elements in the array. All the elements of the array must be of the same type, and here you need to specify the data type of the elements. Then the array name, and followed by the column size. See, not that you need not have to specify the row size. If you recall, in the case of a single dimensional array, only one index is there or one size specification is there. That was not required. Here there are two size specifications. Here the first, or the number of columns, number of rows is not required to be specified, and you have to specify the number of columns, which must be same as the value used to declare the actual array. Here is an example. Here is a function foo which makes a call to bar, and see a two-dimensional array T of size 1 columns and size 1 rows and size 2 columns is declared. So T is a matrix of size 1 rows and size 2 columns. How will you pass? You just pass the name of the two-dimensional array, and in the actual argument you need not have to specify the first size, only the second size. So that's it. So remember that these two functions are sharing the same two-dimensional array in memory. So whatever changes that you are making in this part of the code, that is in this function, is reflected or accessible to this function as well. Okay. So now some exercise problems from two-dimensional array. So you write a menu-driven program with the following options: to read a matrix, to print a matrix, to check whether the matrix is diagonal. Okay, you see the definition of diagonal matrix and see whether the current matrix is a diagonal matrix or not. Another option is check whether matrix is triangular or not. And the fifth option is to check whether the matrix is a magic matrix. So what is a magic matrix? Here is an example. A magic matrix is a square matrix, so that the row sums, here is 15 here again the row sum is 15, row sum is 15, the column sum is 15, this is 1 plus 5 plus 9 is 15, here again 15. Not only that, this diagonal sum is 15 and this diagonal sum is 15. Okay, you just check whether a square matrix is a magic square or not. So what is a magic square? Where the row sums, column sums and the diagonal sum are the same. Okay, and the last problem is to give an option to rotate a matrix to the right or left or up or down. If you look at this instance of the matrix, if you rotate to the right, so rotate right means this column is coming to the first, so right rotation. Okay, and you look at this up, left, down, and right movements of line, and to understand what I mean by rotating on matrix, and uh, and then to it. Okay, so I'm moving to the last part of the lecture, just an abstract discussion on higher dimensional arrays. So we have discussed in detail single dimensional arrays in C and how you can process a single dimensional array and pass it as an argument. And after that, in today's lecture, we discussed about two dimensional arrays. So where you have to specify the size of the first dimension, which is size 1, and size of the second dimension, size 2. So basically matrices, and we discuss how one can process a matrix. And now you can extend it to 3 dimension or 4 dimension or in general n dimensions. Let us look at 3 dimensional array. This figure is copied from the internet, and here look at an array of 3 dimensions with 2 as the size of the first dimension. First dimension index is 1 and 2. This figure is copied from the internet, and they showed it as the first index and second index. And recall that in C, this must be 0 and this must be 1. Sorry for that confusion. And so this is the first index, varies from 0 to 1. You have to decrement 1 from each index. Here 0, 1, 2, here 0, 1, 2, and 3. So this is a 3-dimensional array, and here is how you can access. So the value of the array at first index, this value 0 to this is varying from 0 to size 1 minus 1, and j must vary from 0 to size 2 minus 1, and k must vary from 0 to size 3 minus 1. Okay, of course, if you want to systematically process, you need 3 for loops for I is equal to 1 to n1, where n1 is the size of the first dimension. For j is equal to 0 to n2 minus 1, where n2 is the size of the second dimension, and k is equal to 0 to n3 minus 1, if n3 is the size of the third dimension. So the for loops will look like, for I is equal to 0 to n1 minus 1, for j is equal to 0 to n2 minus 1, for k is equal to 0 to n3 minus 1, you can access a, I, j, k, if a is the name of the array. Now we can generalize this multidimensional array of n dimensions. So how will you declare? This is the formal syntax. The data type, which is the data type of the elements of the array, followed by the array name, followed by specification of the sizes of all the n dimensions, size 1, size 2, etc., size n. Okay, so how will you access? You want to provide n indices to access an element, and the value of I1 ranges from 0 to size 1 minus 1, I2 from 0 to size 2 minus 1, etc., to for In from 0 to size n minus 1. And that's all for today. So looking forward to see the solutions for the exercise problems. Thank you.